Chapter 23. Chapter 23, we're going to look at logarithmic applications. So we've seen logarithms and how we handle them, what they're all about. We've seen the equations, how we handle some of them as problems and expressions. So now we're going to look at the applications of logs. So very important to use and understand logs in a lot of applications. RF in particular, we can find out things like gain and reference, the frequency response of a circuit, creating the Bode plot, which is actually a plot of that frequency response, looking at frequency curves, and then applications to circuitry like our RC circuits that we've already looked at. So the objectives are going to be to compute power and voltage, gains of electrical systems, determine the frequency response, construct a Bode plot of that frequency response, and then compute the charge and discharge of a capacitor. We're just going to do that real quick so that you see what that's all about. You're going to get more of that in your second semester AC Electronics ET132. Because of the logarithmic characteristic, we use power gains a lot. In a lot of cases, we don't use the wattage value. We look at the ratio expression of the power out over the power in, and that logarithmic expression gives us a ratio of a power level and pretty much just gives us a figure of merit, and that figure of merit tells us whether we're in the good range or the bad range. So if we set up that ratio, power out over power in, and take the log of that, what we get back is something called the bell. We get an attenuation of power in the bell measurement. Unfortunately, the bell is too large of a unit for us to use for our applications. It's not practical. So what we have to do is step it down a little bit, and we use something called the decibel. So the decibel is used instead, which is 1/10 of a bell. And the easiest way to do that is to take 10 times the log of the ratio power out over power in. So it's common practice then in industry to leave out the subscript dB. And the only reason that sometimes it's left out is because it is a ratio and it is a figure of merit. And since it is a quotient, when we divide top and bottom, any units that we have, in this case, as you can see, power out over power in, would be in watts. The watts cancel out, so we're left with just a figure of merit. So the attenuation in this case for power is equal to 10 times the log of power out over power in. Well, what if we wanted to solve for either the power out or the power in if we had enough terms that we could do that? Well, just like we've done in everything else algebraically, we start manipulating the right side and the left side until we get what we want. So in this case, if we were trying to solve for, let's say, the power in, I'm going to take the 10 on the right side, move it to the denominator on the left side, and then when I take the inverse log of both sides, I end up with the attenuation divided by 10, and that becomes my exponent for which I'm raising 10 to. And so I have freed up the power out over the power in now that I can solve for power in. So power in then becomes the output power divided by the exponent. If conversely I wanted power out, I move the 10 to the exponential value over to the left side in this case, and it becomes a product of power in times that value to give me the power out. So I can solve for unknowns in a circuit or in an analysis, whether or not I wanted to determine what kind of power in would give me a specific power out, or what kind of power out relates to a factor of power in. So gain measurements then are very important when studying RF systems and circuit. Again, it becomes a figure of merit. A good application then, the proper and efficient cell phone tower placements are very dependent on maximizing the RF power levels in each cell level. You don't want to saturate an area so that you have signals stepping on each other, but you do want to have them spaced far enough apart so that you are maximizing the power distribution and or the sensitivity of your phone to those cell towers. So you can see diagrammatically a block diagram we can put together looks something like this, where we have the power in, the power out, and it's being processed through some type of application, in this case the attenuation. So if we're wanting to solve for that value, it's just as we've seen before, and determining what power in we put into a application, an amplifier in this case, and what we get for a power out. By understanding a few rules then about calculating gains and losses and using the decibel, we can quickly do mental calculations about the system parameters of communication systems. You know, if you're having a problem with Cox Communication, it doesn't seem like you're getting enough signal, and you keep having things drop out on the internet or on your telephone. When Cox Communications comes out, they take a little meter, they open up your line to your house, and they'll put the meter on there and try to determine, do you have enough signal strength? Well, we do this by measuring the decibels. So the power out of an amplifier has 30 watts, okay? So as example, a 30-watt amplifier, power out. The input power is 100 milliwatts. So you can see we've taken something has a very small input, but we want to turn it into a significantly larger output. What is the power gain in decibels? So we want to determine what kind of gain do we have when we start putting this together. So if we put it into the relationship 10 times the log of the ratio of power out over power in, at this point all we need to do is put in our values. 30 watts divided by 100 milliwatts. 10 times the log of that value gives us a value of 24.8, in this case dB. But like I said, you don't necessarily have to put the dB on there, but it's commonly done. Another example, we have a power out from an amplifier of now this time in decibels, dB. If the power input is given to us in watts, 50 microwatts, what is the output power? Okay, so we're converting from decibels to power, and this will be in watts. So if we start with our expression, AP is equal to 10 times the log of power out over power in, we know that the output for the amplifier then in decibels is that 40 dB. Then I take my value that has my ratios in it. I don't know the wattage of the output power, but I do know the input, 50 microamps. So now I begin my algebraic manipulations by moving things around, 10 divided through on both sides, and the log of power out over power in, I'm left with 4 is equal to power out over 50 microwatts. So in this case, if I take the exponential 10 to the 4th, then equals power out over 50 microwatts. That kills the log that we had here in the front of that, so that now we have, let's put that right there, that should be, now we have the log there. We've taken the inverse log, and we're left with 50 microwatts times 10 to the 4th equals power out. And what we end up with is an output power in watts of a half a watt. So we can do some manipulations. What if we're not given power, or we're not interested in the power, but what we're really interested in is the voltage relationships? Well, we can go back to what we learned initially about power being V squared over R and use that same relationship as a ratio. So power out, V squared 2 squared over R out, power in, V squared in over R in. Now I can plug those in for power out and power in into our original expression, and I end up with a product of V squared out divided by V squared in times R in over R out, because we invert here and multiply. So I can break these up into each of the log terms, and now it becomes an addition. 10 times the log of the voltage squared out and in plus 10 times the log of the resistance in over out. If I assume that the output resistance is the same as the input resistance, then this becomes 1 over 1. So the log of 1 is 0, so that term completely disappears. And what I'm left with, I can take the exponent here on the V squared take it out of the terms inside the parentheses, multiply that times 10 like we have here for the power relationship, and now I have an attenuation of voltage, which becomes 20 times the ratio of voltage out over voltage in, and that gives us a new expression that we can use to solve. Excuse me. So now using that expression for gain, using voltages, I can solve now if I know I have a output voltage of 1.73 volts and an input voltage of 50 millivolts. Again, notice, very small input, much larger output. And making that same assumption that the resistance in equals the resistance out, find the voltage gain in decibels. So again, we just run it through the expression. We have the ratio 20 times, we'll go back here, 20 times the log, that should be a log right there. Sorry about that. 20 times the log. If you don't put the log in there, then you're not going to get the right value. So 20 times the log of the ratio 1.73 over 50 millivolts gives me 20 times the log of 34.6, which equals 30.8 decibels. Okay, and another example here, what if I have a gain from a device as minus 6 decibels? The output voltage being 700 millivolts, find Vn. So I start at my same values here. The attenuation then, or the gain, is equal to 20 times the log of V out over Vn. And I'm going to substitute minus 6 decibels for the gain, 20 times the log of 700 then over the unknown Vn that we're trying to solve for. Okay, if I take then my values, then I'm going to divide both sides by 20, and in doing so I get 0.3 is equal to the log of 700 over Vn. Take the inverse log of both sides, I get 10 raised to the minus 0.3 is equal to 700 millivolts divided by Vn. Okay, solving for that exponential, 10 to the minus 0.3 gives me 0.501, and then I can move the voltage in to the left-hand side and move the 0.501 to the right-hand side, and I will solve for Vn to be 1.4 volts in this case. So we now know that given 1.4 volts in, I get a gain of or a loss, in this case, of 0.6 decibels. Reference levels. So when we come back, we're going to take a look at how can I take those gain relationships and reference them to something. So in this case, we're going to figure out what dBm means and using a 1 milliwatt reference level.